Okay, good evening, everyone. Today is the 12th of July. My birthday is coming soon. You're going to find out when is it. Okay, my name is Mr. Chu. Welcome to O-level physics lesson. And we're going to start the lesson on magnetism. And as always, I'll always show you the topical mind map. So can you see over here, physics? Okay, physics. We are at the purple part. So we're ending soon. Magnetism is actually very simple. The tough one will be the last two topics. So today we'll cover magnetism very quickly. Okay, next I'm going to show you all the syllabus. Okay, can you see syllabus? We need to know the laws of magnetism. Can you tell me what's the laws of magnetism? You all have learned this in primary school. Okay, can you tell me what are the laws of magnetism? Okay, Yu-Ting, well done. Okay, two more students, can you all try? What do you remember? What are the laws of magnetism? Correct. Chelsea, correct. How about the rest of you, the boys? What are the laws of magnetism? Okay, Harry, well done. Okay, so for the laws of magnetism, most of you, okay, would already know. Okay, it is the like pole will repel and unlike pole will attract. Okay, I will not write down here, and I will just talk about it in a while. Okay, then we need to know about the magnetic property of matter and then magnetic field. So out of these three topics, you have actually learned everything in primary school. Most of these in primary school. So what are the learning outcomes? Okay, you need to know the properties of magnet, which you have mentioned, like poles repel and unlike poles attract. So north and north will repel, south and south will repel, and so on. Okay, you need to understand what is induced magnetism. Okay, so when you put a magnetic material to a magnet, that magnetic material isn't magnetized at first. But when you put it near the magnet, it becomes a induced magnet. Okay, I'll explain this later on. Okay, then you need to also know the electrical method to magnetize and demagnetize magnetic material. Okay, then number 4, you need to know to draw a magnetic field pattern around a bar magnet and between the poles of 2 bar magnet. Okay, this one you have also learned that in primary school, right? Okay, describe the plotting of a magnetic field like a compass. All these are all primary school stuff. Then finally, distinguish between the property and uses of temporary magnet and permanent magnet, which you have also learned in primary school. So everything that you're going to go through today, you have learned in primary school. Are you excited? We are now back to primary 5. You all learn magnetism in primary 5, right? Not even primary 6. Was it primary 4? I couldn't remember. Okay, give me a moment. Okay, so magnetic field. Okay, these two parts. Okay, magnetic field is these two parts. Yeah, it's quite hard to categorize now. So let me just go to the notes and then we'll start to discuss it very quickly. Let's look at this one. Okay, let's revise back again. Okay, as I mentioned a certain thing, I would like you all to write down some notes. Okay, first of all, you have learned in primary school there are magnetic material as well as non-magnetic material. Okay, the first common misconception is all metals are magnetic material. Okay, that is false. Okay, can you see over here? Copper, brass. Okay, copper, brass, they are all metals. Okay, but they are non-magnetic. Okay, so do not assume, okay, the first common mistake by a lot of people is that you think something is a metal, then it can be a magnetic. Okay, that is wrong. Okay, so all you need to know is magnetic material, namely in O level, you need to know there's 4 main material. Okay, you have learned that in primary school as well. Okay, so the 4 main material is steel, iron, nickel, and cobalt. Okay, iron, nickel, and cobalt are found in your periodic table. You have learned that in chemistry. So can you tell me what is steel? Is steel element? Okay, I'm asking you a chemistry question. Is steel an element? Okay, Qiao Xing, correct, but you need to be a bit more specific, but you're not wrong. Yu Ting, well done. Okay, how about the rest of you? Is steel an element? Can you find steel in the periodic table? Okay, very good. Okay, so iron in the periodic table is Fe. Okay, steel is an alloy where it's majority of iron plus some carbon. Okay, plus some carbon. Is that clear? Okay, so most of the question will be asking about steel and iron. Okay, but you also need to know at your level that nickel and cobalt are also magnetic material. Okay, so when we say magnetic material, when you talk about magnetic material, they are not magnetic. I repeat myself again. Pure iron by itself is not magnetic. Okay, you put iron and iron together, they don't attract. Is that clear? Okay, so you need to make the iron, you need to make a magnetic material a magnet. Then it becomes a magnet. Okay, so there'll be a few ways to make a magnetic material to become a magnet. So there are some ways that you're going to learn. One of the ways is called induction. Another way is called by the electricity method. Okay, so there are different ways to make magnetic material to turn into magnet. So magnetic material by itself, when they are not magnetized, they do not behave like a magnet. Is that clear? But if you put a magnet close to a magnetic material, they will attract. Did I make myself clear? So, for example, if you hang a freely suspended iron, like you have iron bar, let's say this is my iron bar. I hang this, put a string on it, iron bar, not magnetized. Okay, on the string. Okay, it will not actually come to rest in the north-south direction. It may, but it will not most of the time. Okay, so how do you test whether this material is a magnet, has become a magnet? Okay, the test for it will be, there's 2 tests. Okay, the first test is when you freely suspend the magnet to a string. Okay, or you put the magnet onto a styrofoam and put it on the water. Okay, it will always come to the rest in the Earth north-south direction. Okay, because our Earth is magnetic itself. Did I make myself clear? So do you think we have one big magnet inside our Earth? Do we have one big magnet inside our Earth? Can you tell me? Yes or no? So why is the Earth magnetic? Okay, why is our Earth magnetic? Okay, our Earth, in the inner side of the Earth, they are mainly made of a lot of iron. and they are all molten iron, and these iron are moving, okay, inside the earth, and it's very hot. Okay, all these kind of motion of the iron inside our earth, right? Inside our earth core makes our earth magnetic. Okay, next question. This is our earth. Okay, this is the equator. Okay, I draw the earth very badly. We learned that if you are in Canada or Russia or America, right, or in Europe, you are actually at the North Pole, correct? If you are at the like Brazil, South America, Australia, okay, they are actually near the South Pole. Okay, so this is what happens. So if we take a magnet, we hang it in okay, we hang our magnet or use a compass. The North Pole of the magnet will point to the North Pole. Are you clear about this? Okay, so I want to say something very confusing. Okay, so if you have a magnet, if you look at a compass, the red colored dot usually is the North Pole of the magnet. And the North Pole of the magnet will point to the North Pole, the geography part of the North Pole of the Earth. Okay, and then we also you learn that, that's why all of you tell me, like pole repel, unlike pole attract. So this North Pole will point to the north. So this part, this north will attract. Am I right? And then this north will repel the other end. So let me ask you, at the North Pole of the Earth, is it really the North Pole of the magnet? Okay, is the North Pole of the magnet, sorry, the North Pole of the Earth, the North Pole of the magnet? Okay, Yiting say no. How about the rest of you? Do you agree, Yiting? Does the north of the Earth is the North Pole of the magnet? So I did something very confusing, right? Okay, the North Pole usually red color one. Okay, so if I were to draw a magnet in the Earth, for this to make sense, okay, the Earth magnetic North Pole is at the south. Okay, so at the North Pole, we call this the geographical North Pole, but magnetically, it is the magnetic South Pole. Is that clear? I know, very confusing. Just like our conventional and electron current, okay, opposite one. It doesn't make sense. Okay, so for the north of the magnet to point to the North Pole of the Earth, the North Pole should be the South Pole of the magnet. Okay, so the North Pole, the north where Canada is or the Russia is the magnetic South Pole of the Earth. Clear so far? Understand? Now I see the chat, you all say no, no, no. So you understand now? Yes or no? Okay. So next thing is, so the North Pole of the magnet. So if the North Pole of the magnet has to point to the north of the Earth, but the north of the Earth is not the North Pole of the magnet. Is that clear? Then the south pole of the magnet will point to the south of the Earth, and the south of the Earth is the North Magnetic Pole. Clear so far? So the north here we are talking about is the geographical North Pole. Okay, but this area is the geographical North Pole, but it is a magnetic South Pole. Did I make myself clear? Okay, if you are clear, give me a yes reaction. If you are confused, give me a no reaction. Have you learned this? Have you heard of this before now? Is this the first time you hear of this, or your school have taught you before? Can you give me some feedback? Is this the first time you heard of this, or you have learned this before? Yiting said that she have learned before. How about the rest of you? Have you heard of this before? The North Pole of the Earth is the magnetic South Pole. Okay, very good. Because sometimes even teacher also confused. I'm not saying your teacher lah. But this is something that's not easy to understand. Okay, so your school all got teach. Very good, very good. Well done. Okay, so the property of magnet, light poles will repel, and light pole attract. I did not explain. You all should know what this means. Okay, then how do you test for magnet? Okay, how do you test for magnet? Okay, sorry. Okay, how do you test whether something is a magnet? So if I have one thing here and I have another thing here, and if they attract together, can I conclude that they are magnet? Yes or no? Okay, so the only way to test whether if this is a magnet is to use another magnet. Okay, we try one side. So one of the side will have at least a repulsion reaction. If both sides is attractive, it means that this is just a magnetic material. Is that clear? But if there's one side that cause this to repel the real magnet, this means that your material is a magnet. Clear? So the only way to test whether is this a magnet, is to use a magnet and do a repulsion test. Okay, if there is a repulsion, then you can confirm that something is a magnet. Is that clear? Okay, if you are clear about this, give me a thumbs up. Okay, Chelsea is asking me, can I test if it comes to rest in facing the north-south direction when freely suspended? You can use that to test but how do you know whether the direction is north-south? You still need a magnet, right? Then might as well do the repulsion test. Understand? Unless you're able to find a line that is the north-south line, then you freely suspend the thing. Or you can also do that. You freely suspend, you keep on spinning it. And every time it always lies in the one direction. Then more or less you can tell that it's a magnet. But in school, in exam, the proper way to test is to use the repulsion test. Is that clear, Chelsea? Okay, so when two items attract, it means that at least one of these is a magnet. It doesn't prove that both are magnet. Is that clear? So if both are magnetic material, like I told you just now, iron bar and iron cylinder, okay, they are not magnetized. You put them together, they will not attract. Okay, but if one of them is magnetized, become a magnet, and the other one is not, then they can attract. Is that clear? So attraction test cannot confirm a magnet. Clear? Attraction test cannot confirm a magnet. Only a repulsion test can confirm. Okay, so if you are clear about this attraction and repulsion, can you give me a clap? If you understand. Hey, Kwan, are you okay? Hey, Kwan, are you there? Okay, well done. Okay, now a clear reaction. So we have talked about magnetic material. So if a magnetic material is not magnetized, it is not a magnet. Clear so far? Okay, I'm happy to see like 2 questions today so far. That's very good. Please ask more questions. Okay, ask more questions. Surprise me. I don't know everything also. But if I know anything, I will sure definitely teach you. Okay, so next thing we're going to talk about is magnetic induction. Okay, magnetic induction versus the part 3 is different. So magnetic induction is how you make the magnetic material. Okay, for example, okay, sorry. Let me just repeat. If I have a magnet here, this is a real magnet. Okay, so I have an iron nail. If I have an iron nail, so iron nail, if it's far away, it is not magnetic. There's no north pole, there's no south pole. But when I put it near When I put it near a magnet, okay, what happened? Light pole attract and light pole repel. So the presence of the magnet, okay, the presence of the magnet induce magnetism into this iron nail. So we call this magnetic induction. So when I put this iron nail near the magnet, it will attract. Okay, you all learned this earlier on. Okay, when they attract, right, it means that there's at least one magnet. So this magnetic material will attract to the magnet. Then when it attract, this iron nail will become an induced magnet. Okay, what does it mean? It means that you also have the south pole and the north pole. Clear so far? It also become like a magnet. Then if you put another iron nail below, it's able to attract. Then it becomes south pole and north pole as well. Of course, you cannot forever put magnet down all the way. The further it is, it becomes weaker and weaker. Then when you remove the magnet away, both of these will lose the magnetism almost immediately. Okay, so the act of putting a magnetic material near a magnet and becomes magnetic is called magnetic induction. It is not permanent. Okay, it just becomes a magnet because it's being attracted to a magnet. Is that clear? Ken? If you're clear about this, give me a yes reaction about magnetic induction. Thank you, Ryan. How about the rest of you? Beiguan, are you okay? Today, Beiguan we had the slowest. Must be fast, ma. Now later we compete, see who's the fastest. See, test your reaction time. Okay, so we finished about magnetic induction. Okay, then, so magnetic induction is when a magnetic material becomes a magnet temporarily because it is near a magnet. Once the magnet is away, it goes back to become a magnetic material. It doesn't become a permanent magnet. Okay, so we'll talk about two methods of magnetizing a magnetic material to make it a permanent magnet. Is that clear? Okay, so there are two methods that you can see here. Okay, there are two methods. First is the stroking method. Okay, stroking method can be one magnet. It can also be two magnet. Okay, so regardless how many magnet, how to remember? Okay, how to remember? Okay, for me, the way I remember is like this. The pole, the magnet that do the stroking, the pole that leave the magnet will be opposite this material. You know what I mean? So for example, this north pole will move from left to right. Okay, so it leave the right side will become the south pole. Clear? Okay, so you just need to put the magnet, okay, from far away, you bring down, and then you just drag it across the steel bar, then you drag it away, far away. Then you just repeat the cycle again and again and again and again and again until the steel bar becomes a magnet. Okay, so how do you remember the pole? The pole produced at the end of the steel bar is always opposite to the stroking pole, so the stroking magnet. Is that clear? Now, how about we use the two magnet method? Okay, same thing. So this is a steel bar. You're going to do the two magnet method. Okay, so you're going to have two magnet stroking in this way. Same thing, if I use north pole here, I use south pole here. This north pole will go this way. This part will become south. This south pole go this way. This part will become north. Is that clear? So that's how I remember the stroking magnet pole that leave the end of the material will have the opposite pole. Is that clear? So there is a one magnet method, one magnet stroking method. There's also the two magnet stroking method. You all want me to explain the two magnet stroking method to you? Hold on for a moment. I find two magnet stroking. Okay, let me show you all this. Okay, so this is a single magnet method. This is the double magnet method. So can you see here, this is north pole. The north pole that leave the bar will become the south pole. The south pole that leave the bar will become the north pole. Okay, we use a single stroke method. The south pole that leave the bar will become north pole. Okay, you can also do it the opposite way. You put the north pole here, you stroke it away, this part will become south pole. Okay, if you are clear about this, give me a thumbs up. Okay, so if you are clear about the single stroke and the double stroke method, okay, give me a thumbs up. Why I like to laugh? Why are you so naughty? Okay, let's continue. Okay, so this is the mechanical method of making this steel bar a magnet. Okay, next. The electrical way of magnetizing a magnet is to, okay, electrical way is to use a direct current. Okay, the keyword here is direct current. Means that the current can only go in one direction. Okay, you don't use alternate current. So the current is always moved in one direction. So how do you remember which side of the wire is the north pole? Okay, that's the question here. How do you remember which side of the cylinder or the bar is the north pole? Okay, so I want you to see this. Imagine this is the bar. Just imagine. So you can see your solenoid or your coil of wire, okay, is actually around this cylinder. Okay, so when you draw the coil of wire or your solenoid around this cylinder, okay, you know that, okay, you look at this diagram here. Can you see that this is the positive, this is the negative? So current will move this way. So you follow my arrow here. Okay, so the current will flow this way because it's a positive, right? The conventional current will flow this way, and then it go behind and to the front, behind to the front. So what you need to know how to determine which side is the north pole, you use the right hand grip rule. Okay, I repeat myself again. Use the right hand. Do you all know what's your right hand? Your right hand. So imagine this is your cylinder. After you determine the direction of the wire. So in this case, this is the direction that I have determined. Hard to see. Let me just redraw again. Okay, this is the direction of current. So you have determined that this is the direction of the current. So when you put, just imagine, okay, how do you actually, how does the, okay, your finger, your forefinger is the direction of the current. Your fingernail is the arrow. Okay, so you look at this, okay, or one of you take out your pen. Okay, take out your right hand. Okay, put it in front of your face. Okay, in front of camera. Hey, nobody's doing that except me. Okay, take out your pen. Okay, same thing. After you determine how the wire, how the current is moving, if the current is moving from behind to the front, your finger, okay, your finger will move from behind to the front. Okay, then you grip your item, your thumb will be your north pole. Okay, then when you draw your diagram, if the current is from the front go to the back, means the current is this way. Okay, front go to the back. front to back, you grip your material, your thumb points to in this case, my right, which is your left. My thumb direction is the North Pole. So now, all of you look at this diagram here. Just imagine if you were to grip this pole here, your thumb, okay, if I were to draw my thumb, okay, my hand, okay, if I have my finger, okay, this is not a good color. Okay, so this is my finger gripping. Okay, my fingernail, my finger gripping. This is your right hand. Okay, your right hand, my finger is gripping. My thumb will be in this direction. Wait, sorry, the fingernail will not be here. Hold on. Okay, this is your thumbprint. Okay, so if you were to grip, your thumb will be pointing to the right. So your right side is your North Pole. Are you clear about this? So this is the right hand grip rule. Okay, and that's all you need to remember. Is that clear? Okay, this is the right hand grip rule. Okay, if you are familiar with this right hand grip rule, give me a clap. Well, Ryan now give me her love. Wei Kwan always the last to react. Okay, you cannot go for competition. 100-meter sprint, everybody run away, you're still down there at the starting block. Okay, there are also other ways to determine whether is it the North or South Pole. But I don't like the way. You're supposed to look at the wire inside. That one I don't like because it's very hard to explain. Okay, I prefer the right hand grip rule. If your teacher has taught you looking into the side, whether the wire look like north okay, or look like south then that one, if you think it's easy to see, you can use that method. Okay, but I don't like this method to look at from the end, right? You put your eye here. Okay, this is your eye. If you look into this, you look at the wire. If it looks like an N shape, then it is a North Pole. If you look like an S shape, it's a South Pole. Okay, I don't like this method because it's hard to understand. Okay, now let's continue. Okay, so we have learned 3 ways to make something a magnet. So can all of you type out what are the 3 ways of making something as a magnet? Okay, all of you type it out now. Okay, there's some question. Yiting asked me, for the double stroke, can I go in the opposite direction? But instead of stroking outwards, I go inwards. Normally, we don't do that. Okay, all the diagram you see in textbook is all do outward one. So you ask a very good question. You can ask a very good question, Yiting. So as a good scientist, you go and do experiment. Okay, you have a hypothesis, right? You go do the experiment and see whether is that correct or not. Let me Google the question, see whether it was such thing. Okay, I do a quick Google, right? All the example and diagram are all outward stroking. So, Yiting, I'm sorry, I don't answer for that. But it's a very good question to ask. If you're a very curious person, you can go and conduct an experiment. Okay, so for Qiaoxing, you mentioned induction, stroking, and current. Ryan said induction, stroking, and electromagnetism. Okay, the 3 methods will be, the first one is not permanent, it's called the induction method. Okay, the second method is a stroking method. And stroking method, there's 2 types. Okay, the single, or they call it the 1 touch or the 2 touch. Okay, and the last one is by, okay, don't use the word electricity, just say DC current. Okay, the third method, all of you can write down, is by DC current. You cannot use alternating current, you can only use DC current. where the direction of the current is always one direction. Okay, so the third method is by DC current. Clear? Okay, so we have learned how to make a magnetic material to become a magnet. Okay, so this two is the permanent method, and this one is the temporary method. Okay, so let's continue. Then, when you're given a magnet, can you destroy the magnet? Okay, can you destroy the magnet? So when there are three ways of doing it. Okay, first you will heat up the magnet, and then you purposely orientate it in the not the north-south direction. Okay, so if you look at all the example, okay, they always say use the east-west direction. Because if you put the magnet in the north-south direction, the Earth magnetic field is also trying to make it a magnet. Clear so far? Okay, so to demagnetize, okay, all of this method, you put your material in the east-west direction. Okay, so the first method is by heating. First method by heating. Okay, I'm going to explain now. You heat the magnet, and then you put the magnet in the east-west direction. After some time, you will lose the magnetism. Okay, second method is by hammering or by dropping or by hitting. You keep on dropping your magnet, you keep on dropping your magnet, or you put the magnet in the east-west direction and you hammer it, hitting it. Over time, the magnet will also lose the magnetism. Okay, the third method, previously, to make your magnet, to make your material a magnet, you use a DC current, where the current only move in one direction. So if you want to use an electrical method, you have to use an alternating current. Can you see that? Okay, you must use an alternating current. So alternating current means that the current will flow in one direction and then go in the other direction. How many times? About 50 times a second. Okay, so it will disrupt the magnetic pole in the material because the current go one direction then the other direction, and this cycle repeats 50 times every second. So very fast, the magnet will actually lose the magnetism. But that is not it. Okay, that is not it. First, you put the magnet in the east-west direction. There's three steps. Step A, you put the magnet in the east-west direction. The current must be alternating. Okay, and that is not it. That is not it. While the current is alternating, you need to pull the magnet away from the solenoid. So it's a complicated process. Okay, I repeat myself again. The alternating current has three steps. First step not important, but if you want a good way of doing it, okay, you must do the three steps. But the step 2 and 3 are the most important. Okay, first you put the magnet in the east-west direction. You put it in a solenoid with an AC current. Okay, but you don't leave it there. Then after that, you pull it away while the AC current is running. Is that clear? So now I want all of you to type it out. What are the three methods of demagnetizing? All of you tell me now. What are the three methods of demagnetizing? Okay, I go and drink some water. Okay, let me continue. Okay, this is the right hand grip rule that I mentioned just now. And then I told you about the clockwise and the anti-clockwise thing. I don't like this method. I prefer the right hand grip rule. So can you see over here? The current is moving up to down. This plus is minus. So current is moving this way. This is wrong. It should be go up. Okay, so current is moving this way and it goes from back to front, back to front. So your right fingers should follow the direction of this current. So you actually put your, can you see? Your finger is like the current. Can you see? Then your direction of your thumb will be the North Pole. Understand so far? This one are not easy to understand. Wait till you learn the left hand rule. Okay, that's even more complicated. But the right hand grip rule, is it clear now? Is it very hard to understand? Oh, okay. Right hand grip rule can. Okay, there's two right hand grip rule in this topic. So, but the idea is the same, so no problem. Okay, next. Okay, so the thing is this, if you look at the thing, it looks like I don't like this method. Okay, if you understand this method, okay, go ahead. I always confuse and very hard to see. Okay, what you're supposed to do is your eye look in this direction. If it is this way, if your current is moving this way, okay, if it's anti-clockwise, this way, it will be North Pole because it looks like N. Okay, I don't like this method, but if you like this method, okay, go ahead. No one is stopping you. So can I ask the poll, which method do you prefer? Tell me number one, the right hand grip rule, or number two, the look like north and south one. Okay, write that down. Which method do you prefer? Let me get a feel of what you all prefer. I myself prefer the right hand grip rule. Looking at the north and south, very hard for me to see and remember. Okay, thank you, Yi Ting, Wei Kuan, and Hao Rui. How about the rest of you? Okay, Oscar prefer the first one. Did the teacher in school teach both method to you? Did your school teacher teach both method to you? Okay. Wei Kuan say your school only teach right hand grip rule. Okay, now let me go to this thing called the magnetic field. All of you are expected to know how to draw magnetic field. Is that clear? Can? Okay, all of you are expected to know how to draw magnetic field. Okay, so before I go into this example, let's start with a North Pole, which doesn't exist in the world. If this point is the North Pole, okay, the field will always be coming out. Okay, do you remember your the electric field diagram? So North Pole will be something like this, but there's no such thing called the North Pole by itself. Okay, so okay, never mind. Since there's no such thing, we shouldn't learn this. Okay, so what we have learned here, the magnetic field itself is exactly like you have learned in electric field. Just remember last time, we have a plus and a minus. How does the electric field look like? You go this way, this way, this way. Do you remember this? Oh, sorry, I draw wrongly. It's going out, going out, going out. Okay, then here is going in, here is going in. Okay, this is the electric field diagram between a plus charge, positive charge, and a negative charge. Clear? Between a positive charge and a negative charge. So you just need to replace the plus with north, the minus with south, and all these diagrams will be exactly the same. Okay, so you have learned how to do a plus pole here and the plus pole here, two positive charge. You'll get the same same pattern. Or you have a plus here, minus here, and you got a plus here, minus here, you'll get the same pattern. Is that clear? So the idea is the same. Plus will go to minus. In this case, north will go to south. Okay, so the idea is for magnetic field lines. Previously, you learned electric field lines, right? They are all the same. Electric field line is when the line moves from plus to minus. So for magnetic field line, it actually move from north to south. Okay, so far. And before that, you also need to, you are also expected to know the definition of a magnetic field. Do you remember previously, I give you the definition of the gravitational field? Okay, then you also give you the definition of a electric field. And today, you learn the definition of a magnetic field. So basically, their definition are the same, but I just change the word. Okay, so let me just explain to you. What's the meaning of? Okay, so we have learned gravitational field. We have learned electric field. Okay, so electric field is same thing. A region where a body, in this case, you can say here will be say the electrical charge. Okay, experience a electrical force. Understand? So everything is the same, just that for electric field, instead of magnetic material, you put here electric charge. Instead of magnetic force, you use electrical force. Okay, how about gravitational field? Same thing, same definition. A region where a body or a region where a mass experience a gravitational force. Okay, so if you see the whole three things together, you look at these three things together, do you need to memorize these three things separately? Okay, if you look at these three definitions together, okay, if you are with me since last year, I've been always telling you these three definitions are very similar. Don't need to memorize all three, just need to memorize one, then change the keyword. Okay, change the keyword. At the back is very simple. The middle is just what's the item. The first one is a mass, second one electric charge, and third one is a magnetic material. Understand? Okay, so I've been always sharing with you this is because I do not want you to memorize three different definitions. You just need to remember one definition and then change the keyword. Yeah, because some students, they don't like physics because there are so many definitions to remember. But if you follow me over the past 2 years, you realize that I don't really memorize a lot of things. Am I right? Do you think that I remember or memorize a lot of things? A lot of things about understanding the concept. And once you understand the concept, physics is not hard at all. I'm not saying that it's very simple, but physics is actually not as hard as what a lot of people think. Okay, why a lot of people think it's hard is because they choose to, number one, memorize, and number two, they don't understand the idea, the concept. Okay, once you understand the idea and concept, everything fall in place. Then there's no need to memorize much thing. Then the next thing you do is just practice, practice, so that you can complete your paper in time. Okay, a lot of students don't do well because they cannot complete the paper in time because they also don't have enough practice, even though they know everything. Okay, so even if you know everything, the next step in the next few months before O-level, go and practice and practice and practice so that you can complete in time. Okay, that's my tip to you. Don't just know everything and stop there. Know already and practice. Okay, not just for physics, but for all your subjects. Clear? Okay, so this electric field pattern, you understand? Okay, the other thing I need to tell you is this. If the two lines are very close, so is the strength stronger or weaker? When the lines are very close, the magnetic field is stronger or weaker? Okay, well done, Yuting. Where are the rest of you? Xiaoxing, well done. Hao Rui, well done. Any more comment? If the field lines are close to each other, is the magnetic field stronger or the magnetic field strength stronger or weaker? Okay, Hao Rui, well done. Ryan, well done. Okay, so here is stronger compared to here, very far apart, right? So here is weaker. Clear? Understand? Likewise, you compare here and here. The longer gap here will be weaker compared to here. Is that clear? Understand? Okay. Make. Then we are end ready. Okay, magnetic shielding. Okay, what does this mean? What does this mean? Magnetic force, okay? For example, in this case, if I put my iron nail here, okay, even though this, okay, let me draw again. If I put an iron nail here, maybe about 5 cm from the magnet, okay, this iron nail will be attracted to the magnet. But if I put the same 5 cm here with an iron nail, but in between, I put a soft iron in between. If there's a soft iron in between, this soft iron will act like a shield. Okay, so this iron nail will not be attracted to the magnet. Is that clear? Why? Because the magnetic field coming out from north will go through this shield and then you get out. Okay, so you'll go through, you'll go to left and right, it doesn't go straight through. Okay, it goes through the direction of the shield or the sheet. Okay, so it will not go straight through, so there'll be no magnetic field below, and therefore this is called magnetic shielding. In primary school, you also have learned. If you all put a piece of fuse paper here, okay, it's not shielding, the iron nail can still be attracted. Okay, but in place of the paper, you put a sheet of iron. Then this magnetic material will no longer be attracted. Clear? Understand? Okay, Yiting asked me a question. Is this iron sheet magnetized? Okay, I will say that this iron sheet here is induced. Is that clear? This iron sheet will become induced. When you remove the iron sheet will become a normal magnetic material. Okay, very good question now, Yiting. Okay, so this iron sheet is not magnetic, but when you put it here, it acts like a shield. You put your iron nail below, right? You will not be attracted, even though it's the same 5 cm away on the bottom and the top. Understand so far? Okay, another example of a shield. Okay, I got more questions from Yiting. Let me read. Then will the iron sheet attract the iron nail? Okay, no. No, because it acts as a shield, therefore it will not attract, because this thing itself, okay, the north and south pole is not at the left and right side. But in this case, you ask me which side is the north and south pole, I cannot tell you. It seems like this part is the south pole, and then these two parts are the north pole. Very funny, right? Okay, but this part here, there's no pole. Okay, so therefore, it will not attract the iron nail at the bottom. Okay, this thing, what I've said, it doesn't make sense to me as well. Okay, but that is the truth. But you put an iron sheet down here, okay, it actually prevent the magnetic field from the actual magnet from cutting through. Clear? So therefore, it will not attract, even though this itself become an induced magnet. Here become north pole, here become north pole, but the top side here, that's near the magnet becomes south pole. Okay, but bottom here, there's no pole, so therefore it will not attract. So Yi-Ting, you asked me a very good question that made me wonder whether am I saying the right thing. But you understand what I'm saying now? Okay, but I've never seen this sort of question asked in exam before. And let me admit, what I said just now, I'm not 100% sure. Okay, but definitely for sure is, if you put a nail below here, an iron nail here, you will no longer be attracted to this because this sheet of paper of soft iron acts like a shield. Because this is the thing that is certain. Okay, where is the north and south pole of this shield? I am not certain. Okay, but what is I'm certain is this shield acts as a shield, and if you put a magnetic material below, it will no longer be attracted to the magnet, even though it's close by, even though it's of close proximity. Understand now? Okay, so let's look at the next one. This. Okay. So you have a hollow iron container. So we are looking up, down. Up, down. Okay, so this hollow container, this one is something like a donut or a cylinder itself. Okay. It also acts like a shield. So when there's a north pole coming in, instead of going straight through, you'll go through the shape of the soft iron container and then go out from the other side. So whatever inside you put inside this container will not be magnetically attracted, even if you put an iron ring inside. Okay, for example, your wedding ring is iron ring. Quite unromantic. It should be diamond ring, right? Okay, if you have an iron ring inside here, okay, in this configuration, this soft iron container acts like a shield. So when you put anything inside, any magnetic material inside, you will not experience any magnetic attraction. Is that clear? Okay, so this is another example. Okay, so the last part of today's theory, okay, we are going to differentiate between soft magnet as well as hard magnet. Okay, how to remember? Okay, in chemistry, iron is a pure element. So pure element, if you look at the molecular structure, they are all organized in a very solid in a regular pattern. Okay, whereas compared to steel, which is an alloy, same thing, you have the same iron, but they are actually small carbon within them. Is that clear? So because this is so regular in shape, if you were to try to push, okay, let's say I want to push this way, this atom should not be that hard to be pushed up. Okay, this atom here is not hard to push up, but because of this additional carbon atom inside here, it's harder to push. So in terms of the strength, physical strength, I'm not talking about magnetic strength, the physical strength of the material, iron is actually softer compared to steel, which is harder. Okay, so if you all learn technical, okay, iron material is actually soft. I mean, it's of course harder than your head, but it is softer compared to your steel. Is that clear? Okay, so iron is actually soft because it's a pure element, whereas steel is an alloy where there's impurity inside the structure, so it's harder to push. So from there, why do I say that? So that I can help you all remember that iron, being a softer material, will actually make a soft magnet. Likewise, steel is an alloy, okay, which is actually harder in nature, and therefore it is categorized as a hard magnetic material. Okay, that's how I remember. Steel is harder than iron. So steel is a hard magnetic material. Iron is a soft magnetic material. That's how I remember. Clear? So let's continue. Let's continue. Okay, so for iron, if you were to do the electromagnetic okay, I put the iron inside. Okay, so this thing inside can be iron or steel. But if I were to use electrical method to magnetize this material, if it's iron, it can magnetize this iron very, very quickly. And another thing is, okay, so you can actually magnetize this thing very, very quickly. Whereas if you use a steel inside here, you take a while to become a magnet. Okay, because it is a hard material. It will take a while to become a magnet. Okay, so my question is this. Let me ask you a question. If you want to make a permanent magnet that always will have a magnetic field, do you use a soft material or a hard material? Okay, Yu Ting, well done. Oh, you asked me a very good question that I don't have the answer. Can you go and Google and tell me? Okay, Yu Ting, well done. Howie, well done. Pei Fan, well done. Okay, so if you want to make a permanent magnet, you use a hard magnet because it is difficult to demagnetize. Clear? Okay, so Howie asked me a question. Is nickel and cobalt soft or hard? Okay, to be honest, I do not know. So Howie, can you go and Google and then let me know? Okay, but they will not ask. Usually in the O level, they will only compare iron and steel. Okay, so iron is the soft one and steel is the hard one. Okay, and since hard material makes good permanent magnet, then why do we bother to use iron? Can you tell me? What kind of application is useful to be easily magnetized and demagnetized? Why do you want things to be easily magnetized and demagnetized? Do you have any clue? Why in what kind of practical scenario would a soft magnetic material be useful? Okay, can you all go and think? What kind of scenario will soft magnetic material be useful? Okay, so let me ask you a question. Have you all seen a straight yard before? Where they got this big electrical magnet. Then you bring down to all the rubbish, right? Then you attract all the magnetic material. So that kind of magnet, do you want it to be temporary or permanent? Okay, for straight yard, the magnetic sorter. Do you want the magnet to be temporary or permanent? Okay, Pei Kwan say temporary. Why? Why temporary? Permanent good what? You're forever able to attract all your iron and steel scrape. Why do you want it temporary? Why do you? Okay, the answer is temporary, correct. But why do you want the straight yard, the machine, to have a temporary function? Okay, Pei Kwan, can you share your answer to everybody? Okay, you need to be temporary because you can attract, but you need to use the material, right? So you need it to also drop off the machine. So once you switch off the electric current, the magnetism actually is lost easily, and then all your material can be collected. Is that clear? Understand? Whereas for if you use a steel to attract, yes, you can attract all these things. But once you want to make it, you want to take the item, you start with the magnet itself. Is that clear? Okay, there's one more question to ask you. Let me, if I forgot the answer. So let me go and check it out for a while. Give me a minute. Okay, another thing I want to share with you is this. Because iron is a soft magnet which is easily magnetized, okay, it is easier to use to make a soft magnet to achieve a very strong magnetic field. Okay, so the example of the scrapyard machine, well, that one is very strong magnetic field, right? Okay, it's very easy to reach a very strong magnetic field because it's easily magnetized. Okay, that doesn't mean that hard cannot be strong as well, just that it takes a longer time and more difficult to make it stronger. Is that clear? Okay, so today I've gone through, finished the theory lesson. I have 15 minutes left. Do you want to take a break or you want me to go through some questions? Come, everybody tell me something. You think Bitcoin, what do you mean? So do you all want me to continue with some questions? Or we just end slightly earlier today? Okay, I have one vote for questions. How about the rest of you? We can do question, no problem. Who vote for question? How about the rest of you? Ryan, you always, unfortunately, always my lesson, I will induce stomachache one. How come? Every single lesson, you have induced stomachache. Do I actually help to induce stomachache to you? Mr. Ryan? Can you tell me what's wrong? Okay, a lot of you want questions, so let's. I got no every lesson. Every lesson you tell me at toilet. Okay, you all take a 1 minute break while I set up the U-book and come back in 8:48. Okay, since you one question, we'll do 10 questions today. MCQ lah, so it's not very hard. Okay, so can all of you now welcome back? Do question 27. Okay, tell me A, B, C, or D, and I'll go to drink some more water. Okay, Yiting, Xiaoxing, Oscar, and Ryan, all correct. How about the last two students? Ray, correct. Last one. Who's the last student? Hey, Kwan, what's your answer for this? Hey, Kwan, are you there? Hey, Kwan, where are you? Okay, do you all remember I told you this? When the lines are closer to each other, you have a stronger magnetic field. And where the lines are further apart, it is weaker. Okay, so everybody is correct. Bei Kwan, can you try again? Okay, where the lines are closer, it is a stronger magnetic field. Where the lines are further apart, it is weaker. Bei Kwan, can you try again? Bei Kwan, you're stuck, is it? Okay, Bei Kwan, can you see here? K is this far apart. L is this far apart. Okay, hold on. Hold on. Can see or not? Okay, let me zoom in. Okay, can you see? K here is this far apart. L here is this far apart. M is this amount apart. So which one is actually very close? The closest one will have the strongest magnetic field strength. Okay, because when they're all very close, they are very strong. When they're all very far, it's very weak. So, Bei Kwan, can you try again? Okay, well done. So for this answer, the answer is B. Okay, because M, the lines are very close to each other, so the strength is very high. Whereas at K, it is far apart, so it's weaker. Understand? Can Okay, next question. Okay, do question number 36. You may begin. Yi-Ting correct. Hao Wei correct. Xiao Xing Ryan incorrect. You all know why, Ryan? Okay, so these two are not magnetic material, so they will not become a magnet. So the question is this. This is a hard magnet. Sorry. This is a soft magnetic material, and this is a hard magnetic material. So this is easily magnetized. So it will give you strong magnet easily. Is that clear? This one is hard to magnetize. So therefore it will become to become a strong magnet. It is actually harder. Ryan, copper is not a magnetic material, so copper cannot be magnetized. What you tell me about copper? Okay, so iron is easily magnetized, so it therefore is easier to produce a stronger magnet. Understand? Okay. Next question. Question number 27. Okay, you want me to begin? 27. So can you see magnetic question, no calculation, right? All fact question. Okay, this one should be quite easy, right? Okay, Yiting, well done. Well done. Oscar, well done. Xiao Xing, we are talking about okay. Okay, for this question, I have not taught you all before. Okay, we can skip this question, but let me explain to you. If this is a wire that is going into the page, okay, this is going to a page. This is a wire coming. Okay, sorry. I repeat myself again. When you see a pointed dot and a circle, it means that the current is coming from the page and out of the page. When you see a circle and a cross, it means that the current is going into the page. So how to remember? Okay, just remember an arrow looks like this, correct? Arrow like this. If your eye look at the front of the arrow, you will see a dot, correct? If your eye, sorry, if your eye were to look from the back of the arrow, you will see a cross. Okay, so when you draw a diagram where a current go into the page, you draw a cross. It's like you look at the back side of the arrow going into the page. Whereas when you see a dot, it's like an arrow coming out to the page. So this is the picture where the current is coming out of the page. So the current is coming out, the current is going in. So I'm going to teach you something. Electricity and magnetism, you have learned until today from me, and all the things you learned before, not from your school, but you learned in primary school and lower sec. You learn electricity and magnetism separately, correct? However, it's not the case. Both electricity and magnetism are actually brother and sister. Okay, brother and sister, they are actually linked together. Okay, so imagine you have a current coming out of the page. So can you just all take out your right hand? Okay, you point your thumb out of the page. Your finger will be the magnetic field. Okay, this is the same right hand rule. Okay, the right hand rule. So if I were to point my thumb out of the page, okay, my magnetic field, so this is my current, my current is going out, okay? So my magnetic field will be like my fingers, okay? If I point out, my thumb point out, okay, my magnetic field will be in this direction. Okay, you induce a magnetic field. You'll learn that in the next topic. Likewise, if your current is going into the page, your magnetic field will be in the other direction. Okay, you point your thumb into the page. Can you see your finger? It's at the other direction. So it's the same, you're using the right hand. Okay, so a magnet can produce, electricity can produce magnetism. Likewise, okay, so in this case, you see, electricity can produce magnetism. So when you have a solenoid, okay, instead of a wire, you have a solenoid. It can also produce a magnetic field around it. So in this question here, they're asking you, what is the magnetic field that is being created when you have a source of electricity? So having said that, what is the answer for this now? Your answer should be, okay, this solenoid is electricity. electricity produce a magnetic field. So what is produced? Your answer should be a magnetic field. And what's your answer here? So all of you try again. Electricity will produce a magnetic field. Okay, a current will produce a magnetic field. So which of these four answers is the definition of a magnetic field? Can you give me the answer now? Hurry, hurry. Hurry, correct. How about the rest of you? Which of these answer explain a magnetic field? So a magnetic field is a region where what? Where a magnetic pole experience what? Okay, Pei Kwan, try again. Qiao Xing, try again. So what I'm trying to say is that electricity will always produce a magnetic field. Okay, so what field is produced when you have electricity? So the answer should be a magnetic field. So which of these four answers describe a magnetic field? Okay, Pei Kwan, well done. Qiao Xing, well done. Where's the rest of you? Okay, very good. Okay, so in this case, remember, please remember that current produce a magnetic field, and therefore the answer is C. Okay, answer is C. Okay, current produce a magnetic field. Is that clear? Okay, next question. Okay, do question number 33. Okay, now can you all try now? Try. This one should be easy. If you have listened to what I said just now, you should be able to do this question. Okay, I'm very confused again. Okay, all the answer you all gave me previously, ignore. So can you please answer again? Can you type down the question 33? What's the answer? Because I do not know whether you're answering me the previous question or the current question. Okay, Oscar, well done. Ryan, well done. Oscar, well done. Yu Ting, well done. Okay, the last three students, what's your answer? Qiao Xing, well done. Hao Rui, well done. Pei Kwan, you're always the last one today. What happened to you? What's your answer? Okay, so that's me repeat. Pei Kwan incorrect. Okay, Pei Kwan, I want you to go and listen to my lesson today, because I don't think this is what I mentioned today is difficult for you. And if you were to tell me that you're worried for your exam, I do not know why are you not paying attention. Okay, I mentioned before, the north is the north pole, right? When you leave the place, this pole itself should be the opposite. Okay, so y should be the opposite of north. Your y should be either B or D. Okay, but the steel itself cannot have the same pole, so therefore the answer is B. So Pei Kwan, I've been explaining this in detail, the single touch method and the two touch method. Why are you not paying attention? Okay, today you're answering very, very slowly. And now you're giving me answers that's all not telling me that you're not listening in class. Okay, later, Pei Guan, I want you to stay back and give me a proper explanation. Okay, did I get myself clear, Pei Guan? Okay, let's continue next question. Okay, question 34. Quickly tell me the answer. This is about the soft and the hard material. Okay, so which one is it? 34, what's your answer, everybody? Yiting, well done. Hao Rui, well done. Xiao Xing, you answer. Okay, wait. I also blur. Okay, Yiting, well done. Ryan, well done. Bei Kuan, well done. Xiao Xing, well done. Okay. Ryan, can you go and watch the end of the video? Okay, Ryan, before you go, tell me the laws of magnetism. Okay, very good. All of you got it correct. Okay, the answer for this is B. Okay, I will not explain this. Okay, all of you know the answer. Okay, let me quickly go to the last four questions quickly. Okay, 2016. Number 36. Okay, quickly tell me, 36, what's your answer? What material is used for the needle of plotting compass? Xiao Xing, well done. Yiting, well done. Hello, Ryan. When did I talk about Lenz law and Faraday law? Okay, you may go. Bei Kuan, well done. Hao Rui, well done. Oscar, well done. Ryan, what's the answer for this? 36. Ryan. Okay, because you want to make a compass, so a compass should be made of a permanent magnet. Okay, you should make a permanent magnet. Okay, so therefore for this question, your answer should be D. Okay, the answer for this is D. Clear? Okay, very good. Last three questions, 1729. Okay, all we do question on 29 now quickly. Okay, Xiao Xing correct, Yiting correct, Hao Rui correct, Oscar correct. What else? Who else? Bei Kuan. What's your answer? Okay, let me quickly explain. Direct current is definitely wrong. Okay, direct current is definitely wrong. You don't insert it into the solenoid. Okay, so A and D, what's the correct answer? Okay, Bei Kuan incorrect. Okay, so you need to do is you must use the AC current. This is definitely correct. But why is D wrong? You shouldn't quickly withdraw from the solenoid. You should actually slowly withdraw from the solenoid. Okay, so the answer for this is A. Bei Kuan, I really want you to watch this video one more time. Okay? Because you definitely have not been listening to the lesson. Okay, second last question. 2035. The last two questions. Okay, do question 35. Okay, then 36. Okay, you all can answer both questions at the same time. Just put down 35, what's your answer? And 36, what's your answer? Okay, Yuting, well done. You got no question for me, you may go. Okay, Chao Xing, you may go. Wei Kwan, you stay back. Hao Rui, you may go. Well done. Oscar, incorrect. Try again, number 35. Why do you say B is correct? Can a magnet have just the north pole and no south pole? Remember I told you there's no such thing as a pure north pole or the pure south pole. Therefore, I stopped drawing the magnetic field line. Okay, so magnet cannot have just the north pole or just the south pole. That doesn't work. They always come together. Okay, permanent magnet must be made of a hard material. Okay, Oscar. So what is the hard material? Is it iron or steel? Okay, so for 36, oh, we got it correct. The answer is C. Okay, I will not need to explain because none of you got it wrong. So left with Oscar. What is the correct answer for 35? Oscar, incorrect. Between two south pole is light pole. Light pole actually will attract. You remember that? Sorry, light pole actually repel. So there is no force of attraction. Okay, light pole will actually repel. Okay, so Oscar, why you choose all the wrong answer? Okay, the C is the north pole of a magnet can also be the north pole of the compass. Okay, the north pole of the compass, okay, the north pole of compass will always point towards the geographical north pole. But the geographical north pole is the magnetic south pole of the Earth. Understand, Oscar? Okay, Oscar, you may go. Okay, thank you, everybody. I'm going to stop the recording. Okay, good night, and Bei Kwan, you stay back.